I'm Dev, and this session is about some practical techniques to make decisions using data. In my day job, I'm a researcher and data scientist at the University of Washington in Seattle. And if you have any questions, you're welcome to contact me. My Twitter handle is up there and my email address. I try to be fairly responsive. And so we'll be looking at some of the basics behind making decisions, and then 3 common, really headache-inducing problems that we face every day. Buying a car, looking at houses, and healthcare, and health in general. We'll look at different techniques that we can use to make decisions using data. So let's get started. Turns out everybody makes decisions using data already. We all do this in our normal lives. Even the people we know who aren't data literate do this already. We adjust how much we spend based on our bank account balance and our income. We try different restaurants, different conferences, based on things we hear from friends, from colleagues, from review sites, etc. So what we're really trying to do is we're trying to make better decisions using data. And it turns out all decisions have a few things in common. They have a problem. So all decisions fundamentally are trying to solve a problem. If there's anybody here without any problems, you're in the wrong session, go away. Better yet, come up here and trade places, because I'd like to talk to you later. Pretty much all decisions have constraints. Constraints are the limitations on what's possible. We can never have a perfect outcome because there's always trade-offs and options that are unavailable to us. And these constraints are often defined by the problem we're trying to solve, and we'll see a bunch of examples of this later. Pretty much all decisions are trying to answer a question. We start with the problem and we use it to define, and we create questions from that problem. This is a place where we can be very clever, because some questions lead to more accurate answers, and some questions lend themselves to being answered with data that we can get. And lastly, pretty much all decisions are working on, when you look at all the options for making a decision, there's some ratio of cost versus value. Value isn't always just profit or time. It can be a metric that we define, and cost isn't always money. These can be many different things, but we always end up with a sort of ratio between cost and value, which is great because when we are able to quantify options, we're able to pick between them fairly easily. And so to get to that outcome, there are some tools we can use to try and get to this goal. First, there's data. It's the raw material that we can mold with our curiosity to answer questions. Second, there's time. We basically have to spend time to make any kind of decision, to make any kind of judgment. And hopefully, the time we spend is well worth it. We end up getting an ROI on our time to gain something valuable. We're spending time and we're hopefully gaining something valuable in return. And last but not least, we have brains. When I say brains, I don't mean the zombie-style brains. I mean the skills and the curiosity that we can use to work away at a problem until we find a solution. There's a great quote by Isaac Asimov who said that pretty much all great decisions aren't by someone going, "Eureka, I have found it." They're almost always by somebody looking at something and going, "That's weird, that's funny. Why is that behaving that way?" And they work at with their curiosity to find a result. And it turns out that one of the best ways to get good at this, to develop that curiosity and that skill, is to sort of work at it. There's like all famous problems, there's an XKCD about it, which is fundamentally one of the best ways to get good at data analysis and making decisions is to pick a problem you like and work at it using your own time. Or ideally, you're working in a place where the problems that you're working on are the ones you're passionate about. And so this is where a lot of people get stuck, because they get really excited and they get really enthusiastic, and they try and come up with a perfect solution. And they get immensely stuck. I see this with new analysts and new researchers all the time. They're too ambitious in their work, and so they try and explore so many options simultaneously that they never get anywhere. They don't produce any output because they're trying to come up with something perfect. And so what we're really looking at is what I consider the decision cycle. Any decision problem is fundamentally done in some steps. First, we have a problem, and we use it to identify a question. At the very beginning, it's a vague question, and as the cycles go on, we get more and more precise. Then we collect data, and we do research on that data. And finally, we do some analysis on the data we've collected. And after the analysis point, we actually have a choice. If we've run out of time, or if our answer is precise enough, we can choose to stop and make a decision. If we still have more time, and we need a more precise question, we can repeat the cycle over again. This right here is how you can make incremental progress without getting completely stuck trying to find a perfect answer. Oh, and there have been a bunch of studies looking at scientists and researchers and business analysts, and what they found is that these periods of time these steps don't take equal amounts of time. Asking a question takes about 10% of your time, going from a problem to a question to a definition. Collecting the data and cleaning it up is about 80 to 90% of your time. Right, so that's where you're going to be spending most of your effort. Anybody who's ever had a data cleansing job knows just how horrific that can be. Doing analysis, and also all the machine learning algorithms in the world sort of fall into this analysis bucket, is again about 10% of your time. Okay, so that's enough of the basic theory. Let's jump into a problem that everybody hates, which is buying a car. People enjoy this process about as much as oral surgery or the US Congress. It's expensive, it's emotional, and the process is incredibly vague, so it's really easy to feel like you're getting ripped off. And so let's look at car buying as a problem that we can solve using data. So first, we need to define a problem. We can start by defining a problem as, I need a new car, when a more accurate statement is, I need to be mobile to communicate, to commute and be social and get groceries and things like that. That way, we can look at other options. We can look at things like public transportation or cycling. If you're going to bike, by the way, wear a helmet. This guy's just asking to end up on the side of the road. Anyways, a thorough analysis of these options would present many more choices than just buying a car, but this is kind of a short presentation, so we're going to skip that. The other thing that happened was there's been some research. This is from an article in The Atlantic yesterday that looked at the amount of time people spend getting to work and how they do it. And that giant bar on the left is commuting on their own. So most people commute and get to work and spend most of their time in a car on their own time. That's why we're looking at cars. Okay, so what are some of the constraints for buying a car? So first of all, not all cars are created equal. We already know this. They differ in things like features, in quality, their safety ratings, and especially how reliable they are. They all wear down. Cars are incredibly complicated physical machines, so they have a finite lifespan, and it's fairly rare to hear of a car that lasts more than about 300,000 miles. Nowadays you can find cars that last up to about 200,000, but that seems to be the upper limit that you can reasonably expect. And we'll quantify that later. Also, the biggest expense for owning a car is the car itself. It's not the gas, it's not the insurance, it's not the repairs, it's what's called depreciation, which is the cost that you buy it minus the cost that you sell it for. It's the biggest expense to owning a car. So let's quantify that. We're going to jump to, oops, here. Here, actually. So this shows every single car model that was on sale for every single age, starting from when it was brand new, which is on the far left, to something that's 9 years old. So this is over 1,200 different car models that are for sale. And what we can see is that prices drop with age. That's probably not surprising to very many people either. What is interesting is that how quickly they drop is actually a fairly stable relationship. So this is the exact same graph revisualized, looking at what is the percentage drop from year to year. And this is important because when we were talking just now, we were looking at how cars can typically last over 100,000 miles, 200,000 miles is fairly normal. And people normally drive their car between 12 to 12,500 miles a year. That means if you buy a car, it will likely last you about 16 2/3 years, almost 17 years. That comes out to a depreciation in value of almost 6% a year. Right? So if this was perfect, if price moved perfect with value, it means that the price of a car would drop 6% a year. But it doesn't. It drops a lot faster. We can see here a one-year-old car. This is actually by brand, but one-year-old cars drop anywhere from about 10% to about 40%. And 20% is fairly typical. And so what you're seeing here is the value of a car drops 6% a year. The price of a car drops 20% a year, roughly. Oh, all of this data is public. It's open source. You're going to see the link at the end of the presentation. So you can play with this on your own time. Wow, I just lost my... That's just terrible. Okay, so what we're seeing here is the price drops faster than value. So now that we have a problem and we have some data and we know some of the constraints we're working with, we can see, oh, there's one of the constraints, sorry. Most cars are purchased within 100 miles of where the owner lives. So most car markets are local. It turns out the worst place in the world to buy a Prius is in Seattle, by the way. It's massively expensive compared to any other city. Anyways, so now that we have looked at a problem and we've looked at some of the constraints that we can't get around, we can look at defining some questions. And so a very common question that I hear all the time is, what's the best price of a new car? A refinement of that question is, what is the best new car for my needs? And then a refinement of that question is, what's the best car, new or used, for my needs that's on sale right now within 300 miles of where I'm standing? Oh, and it needs to cost less than this price. All of a sudden you start to see, okay, this is a problem that I can attack using data. And that word best, by the way, you'll see over and over again, it implies value of some kind. So if we're looking at the ratio of cost to value, again, that's true of all data problems. When we look at cost, what we're really looking at is the total cost of ownership. It's the total cost of owning a car, including things like gas, insurance, repairs, buying the car itself. So we have a definition for cost. Any DBAs or IT administrators in the audience are very familiar with total cost of ownership. It turns out computers cost way more than just the cost of the physical machine. You have to power it and cool it and things like that. Value is a little harder to define, because when people think of cars, they have emotional attachments to them. But fundamentally, at its very basic level, what a car does is it saves you time and energy compared to walking. So when you're getting a car, what you're really getting is this utility that saves you from walking 200,000 miles. And so when we're looking at ratio of cost to value, we suddenly have a metric we can use. It's the dollars per miles expected, or miles remaining. So that's the total cost of ownership in dollars versus the number of miles left on the damn thing. We need data, and it turns out we have lots and lots of data. It's in many, many different places. There are car advice sites left and right. There's information, if you look for it, about how quickly different car brands die off. And by die off, I mean the car is a wreck. It costs more to repair than it does to buy a new one, at which point it's basically dead. We have information about how much people drive each vehicle, and we have information about how much everything costs. Unfortunately, none of these are always perfectly trustworthy. There's lots of bias in all of this information. And we'll get into a little bit later how we can account for that bias and sort of take care of it and come up with a good result despite that information, despite that. We have time. This is one of the places that I like to emphasize a lot. People are actually more productive if you give them a time limit because they don't dawdle as much. And if we're looking at time, the best rule I've ever heard is take your hourly rate that you make it work and multiply it times 10. For me, that's about $400 an hour. If a car costs $25,000 to $40,000, and I make $400 an hour at 10 times my going rate, that comes out to 62 to 100 hours. That's a long week's worth of work. And that's about as much time as I'll spend on any analysis for something that costs this much. And that is a great way of looking at things because what you're basically saying is the amount of time you spend on any kind of analysis or decision setup should scale to the price. That makes sense. We don't spend a week deciding what to order for lunch. And we do spend weeks deciding what kind of house to buy. So, and we'll break this analysis into three steps: car models, their age, and specific vehicles for sale. So now it's time for another demo. Let's see if I can actually make this thing work this time. Okay, here we go. So this shows reliability versus age. And what we can see here, wow, it's just adjusting all over the place. What we can see here is that different makes and models have different rates of reliability. This isn't that surprising. And the metric we're using is what I call the 5-year death rate. And that is the odds as a percentage that your car is going to die 5 years after you buy it. So if you buy a new car, the odds that it's going to die within 5 years are usually less than 2%. Up here, if you buy a car that's 9 years old, you've got a chance of it dying that's almost 1 in 4 for some of these brands. And again, this information, it's kind of hard to find. It's buried in PDF files and whatever, but it's out there if you look carefully. And it turns out this is great because we can use this to figure out how many miles are left on a car. If I buy a car that is supposed to that has a 1 in 4 chance of dying, and I'm going to be driving it for 100,000 miles, I'm not actually going to get 100,000 miles. I'm going to get 75,000 miles on average because 25% of the time it's just going to die. So that gives us the expected miles left if we include how reliable it is. And we already know how much cars cost. There's a lot of information saying a car that's 5 years old, that's this make and model, costs this much. And so what we can see here is, here are the cars for how much they cost per mile versus their age. And this per mile is actually adjusted for how many miles it's left based on its death rate. So this is just, and so we can actually start filtering this immediately. Let's start dropping down to cars that are fairly inexpensive. And I'm fairly risk adverse, so I'm going to drop down to cars that die less than 5% of the time. I'm okay with a 1 in 20 chance of something dying in 5 years. And I'm going to drop its price down to, let's say, $10,000. And all of a sudden, I have a much smaller list. Of that 1,200 options, I've narrowed down to a few dozen that I can look at, that I can be more specific about. If I go even further, if I want to be even cheaper in how much things cost, I can drop down, and then all of a sudden I have, 5 to 6 options. It turns out the human brain can fit 3 to 7 things in working memory. So if you try and fit more than 7 distinct items in your head, what you're actually doing is you're paging out. So you'll be far less efficient. This is actually one of the reasons why data visualization is so beautiful, because as David McCandless was explaining during the keynote, our brains are designed to look at patterns. A single pattern isn't 100 elements, it's 1 element. So if we zoom all the way out here, what we're actually seeing is this sort of curve, and there's a few outliers above and below. All of a sudden, we're looking at 3 elements in our head, not 1,200. If we look at this exact same graph, but all of a sudden we include the cost of fuel, of insurance, and repairs, all of a sudden it's not this curve anymore. It's more flat. And that's because older cars need more maintenance. Oftentimes their gas mileage isn't as good, and they cost more to insure. So again, if we start dropping things down, and we're going to drop the death rate down to 4% this time. There's still quite a few options. We can go even cheaper. And all of a sudden we have, again, a few dozen options to look at. So this is looking at how to buy a car using data, using information that's publicly available. Getting all of this data takes quite a while, but it's worth it. It turns out this particular analysis took me about 30 hours. So it took me half my week that I was willing to spend. And that was worth it, because all of a sudden it went from, I have no idea what to get, to I have a much more precise answer. A couple years ago, I did this myself. And here we're going to get to one of the really fun little algorithms that I like to use. So earlier, we ran into a problem where there are tons of different data sources that are incomplete. They have bias, and we don't really know which of them to trust. In fact, we usually don't trust any of them. This is a common problem in machine learning, where you have many, many different models, and all of them are only partially accurate. And the approach that people have come up with is what's called ensembling. It's also called model average or bagging. And what it does is fairly simple. It takes many different options and averages them, or counts them. There are more advanced versions of that where it takes the ones that are more accurate and overweights them. And we can do this with cars, because, like we were saying, there are many different car advice sites. So I didn't really know who to trust. And so what I did is I looked at everybody. I looked at places like Car Talk, Edmunds, Cars.com, Cars.com again, the resale value. There was some survey about greenest cars, an Insurance Highway Institute safety website, Forbes, and JD Power. And I basically said, which of these cars falls into sort of like the top 10 or top 20 lists? And then, because I couldn't trust any of them, I just counted them. And so what we can see here is, I was basically looking for a family sedan. These are all of the cars by how many sort of plaudits or awards they win across very popular sections of the internet. And all of a sudden, instead of having a few dozen options, I have only about a half dozen, 7 or 8. And then down here, I have options that have almost no awards. So if I was to look for who to trust, this is a way to trust everyone in aggregate. There's actually a lot of research showing that this is more accurate than most. If you have a problem and you don't know how to make a decision, one of the best ways to make that decision, or to get an opinion, is to collect everybody in a room and ask for them to vote, or ask for their opinions and average their opinions. And that's often more accurate than any individual is alone. You might want to be careful explaining this to your managers. Oftentimes you have highly paid managers to make decisions on their own, when it turns out all the research shows that you make more accurate decisions by basically taking all the entry-level folks and asking for their opinions and aggregating them. You don't really need highly paid managers. Okay, so now that we had car models, let's look at specific cars that are on sale. Well, here we go. So this was the second half of my analysis, back when I was looking for a car. I collected the information about every single car for 2 different car models that were on sale within 300 miles of where I was living in Seattle. And then I came up with a bunch of information around things like, what on earth? A bunch of information about things like mileage, how much I'm paying for the mileage, if it has a warranty, what is the warranty worth to me? There's a thing called replacement cost, which is great. If you don't like a color, then what you're basically doing is you have the option of paying a certain amount of money and painting your car again. If you don't like a warranty, you can buy third-party warranties. So all of a sudden you can take apples and oranges and turn them into equivalent things. And at the very end, I did a bunch of Excel math. I have no idea what's it doing. Okay. And came up with what I call, which is basically a score, which is mileage plus age plus warranty plus basically how accurate the cost is going to be. And this suddenly is seems very simple. Once you start doing this, this gets really easy because you have a bunch of options. You have a couple options that are terrible, a bunch that are sort of in the middling. This isn't really surprising. There's a bunch. What you'll see is you'll see some really bad eggs, a bunch of stuff in the middle, and up here, a couple of options that kind of stand out. They're unusually good. And this is great because what we're trying to do is we're not trying to solve car buying for everybody, just for one person. So we can pick the best options. Oh, and that information about how to get used car prices, this is the actual code that does that. This is about 30 lines of Python code. And what it does is it basically scrapes information off of a web page and then uses a library that's built into Python that you can use for Python that starts ripping little elements out of it. And so what we're actually saying is this big chunk of code here, that's all of the HTML parsing. It writes it out as a pipe delimited file. And this is just an iterator. And so you'll probably have to write lots and lots of this because, like we're saying, lots of data is in different sites. Some of the sites you have to sort of collect manually. That's what I did for car reliability. Some of the stuff, when you have hundreds or thousands of options, you have to scrape it yourself. There are some places like the federal government where you can download CSV files. They're relatively rare. Actually, that was the last demo for that. Aha! So now we jump to houses. Right? Now that we have a car, we've figured out how to buy a car, we're going to jump to housing. So the fundamental problem with housing is we need a place to live. Seems fairly straightforward. Some place like that will probably do. And so when we look at housing, what we're really asking, again, we go back to taking housing and turning it into a question. It starts with, where do I live? A more precise answer, because a lot of people here are from the Bay Area, is what apartments are available to rent in San Francisco? Right? Because I've heard that's a really nice city to live in. A more precise answer is, what's the best place for me to live that's available for rent in the next 45 days? Because all of a sudden you have time periods involved. And again, there are some constraints. There's that famous joke about real estate, the three most important things are location, location, location. It turns out that's true, but that's misleading. There have been a lot of studies looking at why people live in certain places, and there's basically one huge factor for house purchases, which is the perceived quality of schools. Right? Most parents with families will move to a school, to a neighborhood with a good school district, which is why they're consistently worth more. Another thing that changes with price is the size of the house. We're very used to seeing that. Big houses cost more. So this is a graph of San Francisco rent prices for 2010 to 2012. The number on the left is a little bit hard to see, but the prices basically went from about $2,600 to about $3,600 in 2 years, and this is for all size apartments. And so this ends in 2012. So that, if you kind of look at it, you see that's about $1,200 over 2 years, so about $600 a year. And given the price of apartments, that means that the rent is increasing 16% a year. And so we're looking at constraints for rent right now. So we're looking at what are the constraints available. And one of the problems we're seeing is that it's really hard to find a really cheap apartment in a really nice neighborhood in San Francisco. It's really, really difficult. So we're seeing 16% increases in rent a year. Here is San Francisco's income per person over about what, 17 years? And it went from about 26,000 to about 60,000 or 61,000. Over 17 years, that's about 3 to 4% a year. Let's be generous and say it's 4%. And so what we're seeing is that the price of rent is going up 4 times faster than income. Here's another graph. This is the price of housing in the United States from 1991 to 2005. You know those great Power BI predictive modeling demos? You can see this is a fairly standard hockey stick graph. And so if we used Power BI, what we'd probably see is it would say, okay, there's some seasonality, and it's going to keep going up. What actually happened was this. And that's because there are some constraints at play that almost everybody forgot about. And of course, this put very, very highly paid financial institutions out of business. Because they did exactly what most people do. They looked at a trend and they extrapolated the trend, and they didn't understand that there's some fundamental behaviors at work. In this case, there's a rule, there's a metric at play which shows that the price of rent and the price of a house moves in a narrow band relative to income. And that's been true for over 400 years, as far back as we have data. So what we're seeing here, the conclusion we can draw is the rent is too high. If rent keeps going up 4 times higher than income, eventually it will come crashing back down. This is also true of house prices in the Bay Area. It's one of the elephants in the room. It's also why I'm not presenting on house prices. I'm presenting on rent. Because at some level, I feel unethical about trying to convince people that here's a good way to buy a house when I know it's overvalued. This goes back to when you as an analyst are asked to answer a question and you realize the assumptions are wrong, you can be incredibly valuable by pointing out that the assumptions are wrong. Because there's a chance that you're actually headed for a cliff that nobody else can see. One second. Aha, right. So now that we have some of the constraints about housing, let's look at some of the cost. Right? And this gets really tricky because it's really hard to normalize cost for all of its variables. It costs money, but also it costs different times for commuting. I assume most people here, actually, how many people here can work from home all the time? 3 or 4 people, very, very few of us. So commutes are part of our normal existence. And one of the best ways to sort of equivocate this, or to make this equal, is to look at the time it costs, the time we have to work to pay for the rent, plus the time we spend commuting for that place. Right? If it takes you 6 months to pay for the rent and 1 month to commute for that 6 months, you spent 7 months of your life every year having that place to live. Okay, so then we get to value. What we get for value for a place is basically quality of life. That's the fundamental difference between a house in the middle of nowhere that doesn't have any heat and a nice little pad in San Francisco. It has a quality of life that is actually really hard to quantify. There are some techniques. I will not go into them here because they take years to master. So value here is always kind of tricky. If we look at data, there's a lot of data around here. There's data about neighborhoods. There's lots of data around how much various houses cost, how much they rent for. Commute times are fairly easy to get. You can do a Bing Maps or Google Maps query and says, how long does it take for me to get from this apartment to my office, from this zip code to my office? You have to collect it all. Again, that's why collecting data is 80% of the time, but you can absolutely do it. Finally, we should limit the amount of time we spend. It is fairly common to spend at least $20,000 to $35,000 a year paying for a 1-bedroom apartment in the Bay Area. Again, if we look at the time, like your hourly rate times 10, for me at least, for $400 an hour, that comes out to 50 to 88 hours a year. which means, again, I have a long week's worth of analysis ahead of me before I decide where to live. And when we're looking at things that are personal, there's almost always going to be one metric that rules everything, which is time. It's the one thing we spend that we don't get back. Okay, so here we go. Oops, that's the wrong one. Here we are. This is the median rent for one-bedroom apartments in every single zip code in the Bay Area. Takes a while to get, but once you have it, it's very nice to look at. And what you can see is that the most expensive place to live, surprising nobody, is the city of San Francisco itself. A one-bedroom costs normally about $3,700 a month. It gets cheaper as you go further away. Again, that's not very surprising. Most of us are very used to, most of us live in cities, we see this all the time. The other thing I looked at was the time it takes to commute from every single zip code to either San Francisco or the Bay Area. And what we can see here, and that's what's distance up here. And this shows the price of rent versus the time it takes to commute. I love scatter plots, by the way, because when you have two metrics and you want to see the relationship between them, this is great, because all of a sudden you start to see a pattern. You see there's sort of this L-shaped curve. And then a perfect result is down here. It costs no money and it's right next door to our office. Or it's right next door to all amenities. Again, because of constraints, that's impossible. And what we can see is we're basically doing a trade-off. The closer you get to your workplace, the more expensive it tends to get. The further away you get, the cheaper some of the options are. The best options are actually down in this area down here. There's actually a relationship between them. This is another example of how, by the way, predictive analytics you'll try and sort of fit a curve or a line to something. A line is not the right approach here. Right? You can see it misses all sorts of information. Let's look at the exact same graph using different metrics. Here we look at the median income. Sorry, let me back up a step. The median income for a data scientist or business analyst in the Bay Area is $121,000. That comes out to about $97,000 after your income taxes. And so if we look at it, we can look at the annual cost for each zip code for a one-bedroom apartment in terms of weeks to pay for it, just to pay for the rent. And we can also look at how many weeks you'd spend commuting. This is a 50-hour work week, just in your car moving around. And we can see the exact same pattern. However, we could add these numbers, because all of a sudden we're looking at weeks in both places. So we're going to convert those into months, and we're going to see here, this is the number of months it takes to live in, takes to pay for the rent and commute for every single zip code in the Bay Area. And what we can see is it takes 7.8 months for a highly paid data scientist or analyst to live in the San Francisco area, just to pay for a place. You have the sort of donut of cheaper places. They have a good trade-off of income, distance to commute, the time you're paying for commuting, and the time it takes to pay for a place. And then further out, you have places that are still very cheap, but all of a sudden the amount you're commuting tends to eat up all of your time. And this is great, because all of a sudden we can start just filtering down. And as we start lowering the number of months it takes for us to pay for a place, we start to see places drop out. And if we zoom in a bit, all of a sudden there's these three little pockets of blue. Those are the best places to live just in terms of time. This doesn't look at quality of life at all. Some of these places might be crime-ridden hovels you don't want to go anywhere near. But it makes the trade-off really clear. If you're going from one place to another, how much extra time are you spending in order to do it? Okay, so that's housing. Now we're going to go to healthcare and health. A quick poll, how many people trust your doctors to do what's best for your health? That's about half of you. How many people trust your doctors, again another poll, to find the best price of health and price? I see no hands. None at all. This is interesting. This is actually not very surprising at all. And what happens is, again, the problem statement we're defining is we want to be healthy all of the time and to live as long as possible. When we get sick or when we get hurt, we want to recover as quickly as we can. And this is especially true for things like chronic diseases. It turns out health and healthcare has another big elephant in the room. So this is data from the CDC, from the Center for Disease Control, and it shows the amount that we spend each year in the United States on different categories of disease. The ones that are the most expensive on the far right are almost entirely preventable using lifestyle choices because they're heart disease, chronic lung disease, and diabetes. Then you have diseases that are partly preventable, things like Alzheimer's, stroke, which is often associated with high blood pressure, and end-stage renal disease, which is often associated with old age. One of the things that we see here is that most of the money we spend in our healthcare system is for preventable diseases. They're also called lifestyle diseases. Quick quiz. What is the fastest code in the world? Does anybody know? The fastest code you can ever write. It's infinitely scalable. It's the code you don't write. The fastest code in the world is the stuff you don't write. It takes no time to execute and it'll scale forever. The cheapest doctor visit in the world is the one you don't go to. It is always free. Given that most of the money spent in our healthcare system is on preventable diseases, the best approach we can take to saving money on our healthcare system is not using our healthcare system. And so when we look at healthcare, what we really should be looking at is health. And so the real question we should be asking is not, how do I make doctor visits cheaper? It's, how do I make doctor visits unnecessary? How do I make the medical system unnecessary for me for lifestyle diseases that are likely to be fairly expensive? And it turns out there's some great advice around there. The tried and true advice, which is exercise and food, exercise and good nutrition, is still the best. And so all of a sudden, our question about health isn't how do I find good health choice, how do I find good hospital choices? It's how do I find good exercise and food choices? So we're going to look at one example of that, which is exercise. So what are the best exercises for each of us? The other question, food, is a great one, and I had a demo working on it, and it wasn't working this morning, so sorry about that. So let's look at how we can do this. Again, we're looking at time. So we've looked over some of the constraints. If we look at time, we see that we want to find out how much time should I spend on this? How much time should I exercise, and what is it worth? And it turns out that the top two diseases that are lifestyle related, which are heart disease and diabetes, cost a person about $19,000 a year to treat. That's out of their own pocket. That's not the medical system insurance. That's out of your own pocket. And $19,000 a year, again using our $400, time as money ratio, that comes out to about 47 hours to analyze. So again, a long week's worth of work. And so and also $19,000 is almost 500 hours of your time working, roughly. I suspect most of us make around about $100,000 a year, maybe a little bit more, maybe a little bit less. And so what we see is that $19,000 is about 500 hours of your time. If you can be healthy and avoid those two diseases alone in less than 500 hours a year, you're making more than your job. You're effectively giving yourself a bonus in the future. If you exercise 1 hour a day, which is 365 hours a year, that comes out to about $52 an hour. So all of a sudden, you start to see the ROI of exercise, which is a phrase I never thought I'd have to say. Okay, so let's look at some of the constraints behind exercise. And it turns out exercise has one big one. When most people start a sport or an active activity, they stop within a month. It happens a lot. And so there's been a bunch of research looking at why sports are seen, why exercise and sports are something that people try and start and then stop. And so a lot of the constraints start going from data to things like biology and psychology. And there's a few. First of all, human beings have limited willpower. We have a certain amount of willpower and mental energy we can do a day, and then we're done. Because our brains, at some level, are biochemical boxes. Another thing that they found is that habits are a way to sort of shortcut the system. They're a way to do things without expending mental energy. But developing a habit takes at least 6 months. A lot of people, when they look at exercise, some of the big reasons they give for quitting are it's expensive. Anybody who's signed up for a gym knows this. They are seen as culturally specific. A lot of us don't play things like football or rugby or cricket or hockey because they're seen as culturally not for us. And one of the huge reasons is we have a hard time fitting exercise into our busy, busy schedules. Never mind the ROI, it's just hard to do. I'm seeing some nods. So all of a sudden we have the constraints of our problem. We're looking for ways to be active, to be healthy, and to exercise and play sports but it needs to be enjoyable. It needs to be something we don't dread for at least 6 months during that habit-forming phase. It needs to be relatively affordable, and it needs to be something we can fit into our schedule. And so we can look at exercise as a data problem. So to solve a data problem, we have to come up with cost and value. Cost is fairly easy. The cost of exercise is the money you spend on it and the time it takes to exercise that you're not actually being active. So if you're going skiing, the time you spend driving to and from the ski resort doesn't count. The value is the time you spend exercising and how much you enjoy it. When we're looking at data for sports, there's a lot of it. There's actually Wikipedia articles, the simplest thing in the world, for all sports that are commonly played in any country. There's hundreds of them. There's the cost of each. You can do Google or Bing searches and find what's the typical cost for skiing, for swimming, for snorkeling, etc. There's information about which sports are group sports, which sports can be done individually, and which sports can be done in your city, how popular they are. And for sports that are pretty much always outdoors, there's a lot of weather data. So we're going to look at a few examples of this. So here's a list of over 100 different sports. More importantly, here's the price. Some of them are absolutely free. They cost nothing that you don't already have. And some things are extremely inexpensive. For example, basketball costs roughly $2, which is the cost of a basketball. And we can also see a lot of the most popular sports in the world are up at the top because they cost almost nothing to do, almost nothing to play. This is the annual cost to do it, including the cost of equipment. And down at the very bottom, we see this giant outlier, which is parachuting. It turns out it's extremely expensive if you want to go jumping out of planes. because planes are expensive. Also, nobody in their right mind uses a parachute that isn't packed professionally. And that's expensive as well. So there's a couple of outliers, and these aren't that surprising. Parachuting is extremely expensive. Horseback riding is very expensive. And unless you happen to build a bowling alley, bowling is extremely expensive. However, many of these cost less than $1,000 a year. In fact, most of them cost less than about $300 a year. And there's a lot of very random ones in here. So for example, I've got things like dodgeball. Turns out DDR is extremely cheap. It's very active. And there's a lot of research showing that the best way to stay active is to enjoy it, even if it's something that other people will go, huh, that's kind of weird. This is another scatter plot. This shows the time it takes to prep in hours versus the percentage of time you spend exercising. So the perfect results are down here. They take no prep time. They take no time to set up. And so you're pretty much spending all of your time being active. It's easy to fit into a busy schedule. So there's some very odd ones like unicycling, roller skating, DDR, cycling. There's a bunch of ones down there. If we look at this versus price, again, we see this giant outlier in terms of price, which is jumping out of planes. If we drop down a little bit, let me drop down even further. We can see that the perfect results, again, are down here. They cost almost no time, and they can be done in very small increments. So they're cheap, and you can fit them into your busy schedule. And there's quite a few of them. Cycling, gardening. I don't know why wood carving's in there, but it is. Maybe you can be very active at it. I don't know. And then finally, we have the minimum exercise and the cost in 5 years. So this is very similar to the previous one. And let's actually take a quick look. Let's look at the minimum time we want to do it, which is, let's say we're actually going for an hour a year. Sorry, for an hour a day. And we don't want to spend more than, let's say, $400. All of a sudden, we have a specific list. I am only looking at cost here. I'm not looking at value, because it turns out value is a very personal choice. There is no one sport that everybody enjoys equally, and everyone enjoys a lot. And so when you're looking at information like this, all of a sudden you have to start making your own choices about value. You have to define that on your own. I'm very partial to cycling and Nerf wars, but it turns out they're very cheap. Yeah?
Just thinking on value, would adding calorie expenditure, like that fit in there? And do you happen to look at that slot, look at that sort of thing while you're putting
I looked at that. The problem was calorie expenditure, again, really depends on things like gender, body mass, how active you are, and the margin for error is actually extremely high. So that's actually a fairly great way of looking at how active you are for measuring value, but it's something you have to do on your own. So that's that's pretty much all of my presentation. There's a few conclusions that I'd like to go through. If we look at what are the steps in a data problem, in making decisions using data, we have to have a problem. We need to learn about the constraints. One of the best ways to learn about the constraints is just to read random news articles and blog posts from people who are very active in it, because they will tell you what the constraints are. From that, you start asking questions. Ideally, you want to be as creative as possible to come up with precise questions you can use that can be easily answered using data. You want to define cost and define value for yourself. Oftentimes, it's easier to define cost than value. Value is a very nebulous proposition to a lot of places. And you want to look at collecting as much information you can, as much data as you can, to define cost and value, and just generally what options are there. And when you're collecting data and analyzing it, again, you're doing it in cycles. You are asking a general question, collecting general data, doing some analysis, making a choice if that's enough, and if it's not enough and if you still have time, repeating over and over and over again. Some of the techniques we've looked at are the one big machine learning technique, which is ensembling. At visualizing data, it turns out that one of the things that computers are very, very bad at is relationships between numbers that mean something. Right? It's very easy to write something that writes correlations, that detects correlations. It's extremely hard for a computer to look at 1,000 different correlations and say, this is the one that matters. So human intuition is a huge part of this process. We have to look at manipulating numbers to be clever, to come up with metrics that matter. And we need to choose what features or what variables or what attributes we care about. All of this content is available on my blog and on my GitHub account, which actually includes all of the Tableau visualizations, all of the data underneath it, and this entire talk. Any questions? Yes? I ended up getting... Sure. So there were these two options. The very top one was a Honda Fit. The one right below it was a Prius. I ended up getting the Prius. And it turns out that this was another sort of interesting thing I found. A good way to buy an inexpensive car is to go away from cities. The value of a car is basically inversely the price of a car for a given value is inversely correlated with the median income in that zip code. So, and car dealers know this. That's why you'll see fancier cars and fancier dealerships in rich areas. Which is a little interesting because if you think about it, driving 300 miles round trip, which is basically a long day's work, to save about $8,000, $9,000 seems obvious, but most people don't do it. Don't know why. Other questions? Yes, sir.
Where did you scrape the VIN numbers?
That wasn't scraping. That was incredibly manual. Okay. It turns out that there's a few big sites for what cars are on sale. Auto Trader is one of the big ones. Craigslist is another big one. However, Auto Trader you can scrape. There's actually some great resources for how to scrape Auto Trader using Python and R. Craigslist is a lot harder because there's no standard format for any of the posts. A lot of times the data is actually in images. I've actually looked for how to scrape data out of Craigslist for things like cars or sales, and it's impossibly hard because there's no standard format. So that was actually done manually. Other questions? Okay. Thank you for coming.